Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we are going to prove the theorem that is sometimes attributed to Thales of Miletus. And in this video, we will work through the proof. It's a little bit technical and a little bit difficult, but we'll break it down step by step. Okay, so let's restate the basic proportionality theorem, traditionally attributed to Thales of Miletus, also called the Intercept Theorem if you look on Wikipedia. Actually, both of those names are used on Wikipedia, and a few other names are also used in the literature. Remember, we have these two lines here intersecting in A. We have the points A1, B1, A2, B2, and we have this condition that the lines here, the line A1, A2 and B1, B2 are parallel if and only if the ratios on the sides are equal to each other. So let's talk about the proof strategy first. All right, so as is often the case with an if and only if kind of statement, we're going to separate the two directions of the proof. Right, so we have the implication of if the lines are parallel, then the ratios are equal. And I'm denoting that direction by this forward implication arrow. And the other direction is if the ratios are equal, then the lines are parallel. Okay, the forward direction is quite difficult, actually. And so if the lines are parallel, then the ratios are equal. And we're going to look at three stages to that proof. So the first stage we're going to do, and we're going to do this in detail, is we're going to prove it in the case when A1 is the midpoint of the segment SB1. The next stage, and for this I'm not going to give a complete detailed proof, but I'm going to give an outline of how we prove it. We're going to consider the case when the ratio is a rational number, right? So if I look at SA1 over SB1, and if that's rational, then I will show it's equal to SA2 over SB2. And then finally, we're going to have to make a limiting argument to get it for all possible real numbers for that ratio of SA1 over SB1. Okay, and then the converse, right, the implication with the left arrow, so if we assume the ratios are equal, then the lines are parallel. That one is going to follow by a pretty straightforward application of the argument we've used over and over again, where we are able to say that we construct an auxiliary object, and then using that, we show that there's only one object, and that gives the result. We will talk a little bit more about that, I guess, at the very end of this video, and then dotting every I and crossing every T of that will be part of your homework assignment. Okay, so let's do the first step of my proof outline. And I'm going to call this maybe a theorem in its own right. So we're given these two lines, SB1 and SB2, and they of course intersect in S. And I'm assuming that A1 is the midpoint of SB1. A2 is a point on the line SB2, and I'm assuming that A1, A2 is parallel to B1, B2. And what we want to do is we want to show that A2 is also the midpoint of SB2. And so if you look at our statement of the basic proportionality theorem, this would be the case where the ratio is a half. Okay, so let's go through the steps of this proof carefully. So I have here my picture on the right with all of our givens. So the first thing we're going to do is we're going to introduce a line L prime that is parallel to SB2, and it is incident to A1. And I'm going to make M be the intersection of that line L prime with the line B1, B2. So that's just like in my picture here. And now, by definition, right, my two horizontal lines here are parallel by hypothesis, and this line on the right is parallel to the line on the left by construction of this line on the left. So this red shape here is a parallelogram. And as you recall about our properties of parallelograms, that means that the side A1M is congruent to the side A2B2. And I've named that fact with a little star here. Okay, the next thing I have is that by corresponding angles, right, so this is a version of the alternate interior angles theorem, the angles that I have at here, if I look at A2S A1 and M A1 B1, right, I'm looking at my parallel lines here, A1M and SB2, so my two oblique parallel lines, and I'm thinking of SB1 as being a transversal. And that gives me my first identity on these angles. And then the second identity, right, so I have SA1, A2 is congruent to A1, B1, B2, or A1, B1, M, as I have it written there. Right, so there I'm thinking of my two horizontal lines, A1, A2, and B1, B2, as my two parallel lines, and this line SB1 is the transversal. So now, by side angle side, those two triangles sorry, I didn't mean side angle side. This should be angle side angle, right? Because I'm saying that that side, that's congruent to that by hypothesis, and I just argued by the corresponding angles that these guys are congruent, right? So that's angle side angle. So we'll fix that in the notes. And then from that, right, so I had these two triangles congruent to each other, which means, right, this guy was congruent to that guy by what I called star using the parallelogram, but it's also congruent to that by the congruence of those two triangles that I have here. So that now gives me that A2 is the midpoint of SB2, which is what we wanted to prove. So I gave myself the little QED box. So now we've just finished that first piece of our proof outline of our strategy for how to prove that basic proportionality theorem, also known as the one of the theorems attributed to Thales, or the Intercept Theorem. And specifically what we've proved is this case where we have this configuration of these two lines, and we have SA1, B1 on my line on the left, SA2, B2 on my line on the right, with the points in that order. And we assume as hypothesis that the line A1, A2 that I have here in dashes is parallel to the bottom of this picture, this B1, B2, that line. So if they're parallel, and if A1 is the midpoint of my segment SB1, right? So A1 is the midpoint, then automatically A2 has to be the midpoint of this other side. Right? So it's saying if the ratio on the left is a half, then the ratio on the right is a half. Right? That's a very special case of our theorem. It only goes one direction, for now at least, and it only is for that very specific ratio of 1/2. Up to here, this is a solid proof. From here, going on out, to get general ratios here, right, we want to replace this with some ratio, I'm going to call it, let's say, r. So if I have this ratio r here, I want that to be true for any ratio r. We're not going to prove that in complete generality. We're going to sketch why it works if r is a rational number. And then after that, we will explain how you'd use a limiting argument to make this work for a real number. But that's going to be more of a proof sketch, because dotting every I and crossing every T in this proof is quite difficult and time-consuming. OK, let's go ahead and attack that sketch. OK. The extension to rational ratios is pretty straightforward, except it involves a lot of bookkeeping. So what we'll do here is we suppose that SA1 over SB1 is some rational number P over Q, and I can, without loss of generality, assume it's less than 1 just by swapping the roles of A1 and B1. And now what I do is I slice up the segment SB1 into Q equal segments, and I'm going to call these points, let's say P1, P2, etc., up to PQ. And I'm going to construct all of the lines, all sorts of lines parallel to B1, B2, incident to each of the PJs. And I'm going to construct lines parallel to SB2, incident to each of the PJs. And this is maybe a little bit hard to understand from this text, so let's look at a picture. So here I'm assuming P over Q is 2 over 5, right? Just to give a nice concrete example. So this is my configuration at the beginning of the problem. I have on the left here SA1, B1, and I'm assuming that the ratio SA1 over SB1 is 2 over 5. And so A1 is 2/5 of the way between A and B1. And I have these two horizontal lines that are parallel to each other. Right, those are my givens. So now I slice up, right, I said this was 2/5. So I slice up from S to B1 into these 5 pieces. So I have S, P1, P2, which is the same as A1, P3, P4, and P5. Each one of those is 1/5 of the way down. And now I draw a bunch of parallel lines. So the first set of parallel lines I do are these horizontal parallel lines. So these are the lines that are parallel to A1, A2. And they intersect on the right here in points Q1, Q2, Q3, Q4, and Q5. Now the next thing I do is I make these oblique parallel lines. So I put lines that are parallel here to the line SB2, but incident to P1, P2, which is A1, P3, P4. And now, if you look at this picture, I end up with a whole mess of these triangles here on the left. And basically, by the same argument as we used before, we can show that these triangles here are all congruent to each other, right? That S, P1, Q1, let's say, is congruent to P1, P2, and this unnamed point, A1, or I should call it P2, P3, and that unnamed point, etc. So we end up with a whole mess of congruent triangles. And then we can look at these big parallelograms, or the little parallelograms, argue that all these little parallelograms are all congruent to each other, and use that to argue then that all of these segments on the right are congruent to each other. And that allows us to prove the theorem, in this case, of a rational relationship between SA1 and SB1. So that still leaves the case where the ratio is irrational. So here the trick is we take our point B1 and we put nearby points, and I'm going to call them B1 minus and B1 plus. So B1 minus is a little bit closer to S, and B1 plus is a little farther from S. But I do it in such a way that these ratios are rational. I can always do that. We apply the theorem for SA1 and B1 minus and SA1 and B1 plus. And playing this game and being a little bit careful about things, we can get that the ratio SA2 over SB2 is sandwiched between the two ratios that we had that were rational numbers. And then in taking a limit, this then forces equality, right? Because SA1 over SB1 minus and SA1 over SB1 plus, they both converge to the ratio SA1 over SB1 as I take my points B1 minus and B1 plus closer and closer to B1. So here we do a limiting argument to show the result in that case. Okay, this is a little bit difficult, and to be honest, I don't know how the Greeks thought about this. I should look at that, or you can bring this up in your history of mathematics class. But of course, we now have a modern understanding of limits in order to make sense out of this very carefully. And right, if you buy this sketch, this finishes the proof of the forward direction of our implication, showing that if the lines are parallel, then the ratios are equal. Okay, so now we've sketched the argument in the case of a general ratio. But that's all in the situation where we assume the lines are parallel and then conclude that those ratios are equal to each other. Now let's take a look at the converse. So the converse says, if the ratios are equal, then the lines have to be parallel. So we're going to sketch that proof, and you'll dot some of those I's and cross some of those T's in your homework. Okay, so let's take a look at the strategy for proving that. So we have these two lines intersecting in S, and we have points SA1, B1 in that order on the first line, and SA2, B2 in that order on the second line. And we are given that the ratio SA1 over SB1 is equal to the ratio SA2 over SB2. And our goal here is to show that the lines are parallel. And as you may have noticed in my little picture here, I've made the lines almost but not quite parallel so that we can see what the idea is that we want to do in our proof. You're going to write out these details on the homework assignment, but the basic idea is that you want to construct the line parallel to B1, B2, incident to A1. And this will intersect the line on the right in some point we call A2 prime. You can apply the basic proportionality theorem to that new configuration of points. And here's where the work is, most of the work that you're going to need to do. I want you to conclude that that forces the point A2 prime to equal A2. And from that, you want to say that this line A1, A2, which is the one we started with, well, that's equal to this new line that we constructed, and therefore is parallel to B1, B2 by the construction. Okay, I'll let you write that out on the homework, and I'll say that the key detail that you're going to want to do is the conclusion that A2 prime equals A2. Okay, that's it for this video. Thank you for watching, and I hope you find that theorem and its proof as beautiful as I found it. You're not responsible for all of the details of it, but I will ask you to understand the case when we have that ratio 1/2, so that first special case that we proved. Well, thank you for watching. I hope you enjoyed it. See you on the next video. Happy mathing.